video, we're going to look at continuity. When is a function continuous? A function is continuous at a point when you can draw the graph of the function in the vicinity of that point without lifting your pencil from the paper. So that's an informal definition. We're going to want to look at a more formal way of checking whether a function is continuous. If you take a look at this box here, we have continuity at x equals c. A function f is continuous at x equals c if the following three conditions are satisfied. F of c is defined, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to f of c. So 1 and 2, the values that you get for those should be equal. If f is not continuous at c, then that means it's discontinuous there. So we're going to use that three-step check to check a function for continuity at a specific point. And if any step of the test fails, the function is not continuous. So we just say it's discontinuous at that point. So for example, here we have a function and we want to determine if it's continuous at the x value that's indicated. And here we have the function f of x, and we want to see if it's continuous at x equals 3. So we're going to go through our three-step test. And the first one we're going to look at is, does f of x exist at x equals 3? So here we can see x equals 3, but if I go above, I can see an open circle there. So an open circle indicates that f of x does not exist at x equals 3, right? It's not defined. So therefore, it's discontinuous at x equals 3. Okay, so does f of x exist at x equals 3? No, because the open circle indicates the function is not defined at x equals 3. So therefore, which is what that symbol means, therefore, f of x is discontinuous at x equals 3. How about h of x? So first we want to see, does h of x exist at x equals 0? Okay. So x equals 0 is the y-axis, right? And we know that it does exist here where it's a closed circle at -1. So that's a yes, and it's -1. So then we want to go to our next test, the next step in the test, which is we want to check to see if the limit exists at x equals 0. So we're going to check, in this case, the limit as x approaches 0 from the left, and we want to check the limit as x approaches 0 from the right. So from the left, if I approach 0 from the left, I can see that h of x equals -1. And as I approach h of x, as I approach 0 from the right, I have to look at this piece of the function because that's on the right side. My h of x would equal 1. So this is -1 and that's 1. Now, if you recall from one of our previous lessons, the one-sided limits exist, but they're not equal. So therefore, the limit does not exist, which means that this is discontinuous. You can pause the video and try the next two problems and then unpause when you're ready to move on. Let's talk about the difference between a removable discontinuity and a non-removable discontinuity. And then also, what does it mean to be continuous on an open interval? So a removable discontinuity occurs at a point of the limit exists at that, if the limit exists at that point. Another way to look at it is when a function can be made continuous at a specific point by defining or redefining it at that point. So if you look at example A, for instance, the function's not defined at x equals 3, but the limit as x approaches 3 still equals 2. So if we could redefine the function and we could make it continuous at 3. And that would be if we said that f of 3 was equal to 2. A non-removable discontinuity cannot be fixed by redefining the function. So we can see that in example B. Okay, h of x does not approach a single value as x approaches 0, right? When you approach 0 from the left, h of x equals -1, and as you approach 0 from the right, h of x equals +1. So therefore, the limit as x approaches 0 for h of x does not exist. So it can't be redefined. So we would have a non-removable discontinuity. What does it mean to be continuous on an open interval? So when we say that, use that phrase, we just mean if the function is continuous at every x value in the interval, we say it's continuous on an open interval. Now, two things we need to look at to help us determine continuity in a closed interval is we have to look if the function is continuous from the right which it is if at x equals c, if the limit as x approaches c from the right of f of x equals f of c. And then, of course, f is continuous from the left at x equals c if the limit as x approaches c from the left of f of x also equals f of c. Okay, so we use these things to determine continuity on a closed interval. A function f is continuous on an open interval, which we use parentheses, right, to show open intervals, if it is continuous at every x value in the interval. A function is continuous on a closed interval, notice we use brackets, if the following three things occur. So if it's continuous on the open interval, if it's continuous from the right at x equals a, and if it's continuous from the left at x equals b. Here's an example. So let's determine where the function f of x equals the square root of 1 minus x squared is continuous. Okay, let's take a look at what the graph looks like. So I'm just going to plug this into Desmos. And we've got the square root of 1 minus x squared. So as you can see here, it kind of looks like a semicircle. And you could see that the domain goes from -1 to +1. Now, is it continuous on that interval? Okay, so what we're going to do is we're going to, since we know that it's continuous on that open interval from -1 to 1, because it's continuous at every x value there, right? The domain is from -1 to 1. Now we're going to check to see whether the endpoints are continuous. So let me draw a quick picture of this. Here's -1. Here's +1. Okay, and we can see here that it is continuous from -1 to 1, right? And I know that because I know what continuous means. It's continuous at a point when you can draw the graph of the function in the vicinity of the point without lifting your pencil from the paper. And also, so I know that it's continuous on -1 to 1, the open interval. Okay, but now I want to check the endpoints. So first I want to check the limit as x approaches -1 from the right of f of x. Okay, so as I approach -1 from the right, I can see that it equals 0. And then I also want to check as x approaches positive 1 from the left. So as I approach positive 1 from the left, I can also see that it's equal to 0. Now you might ask why I didn't check the limit as x approaches negative 1 from the left. And that's because there is nothing over there, right? The graph doesn't exist to the left of negative 1. Same reason why I didn't check the limit as x approaches 1 from the right, because the graph doesn't exist over here on the right, okay? Now, since both of these are equal, my one-sided limits, I know then that and I also know that it's continuous on that open interval. I know that the graph is continuous then on the closed interval, negative 1 to 1. So therefore, it's continuous on the closed interval negative 1 to 1. And again, we use parentheses for open intervals, brackets for closed intervals. This table shows some key functions and tells whether or where each is continuous. So for polynomial functions, it's continuous for all x. For rational functions, it's for all x where q of x does not equal 0, right? So the denominator, when we looked at rational functions, remember we don't want the denominator to equal 0. So of course the function itself is continuous for all the x values where it doesn't cause q of x, the denominator, to be 0. So here you can see the vertical and horizontal asymptotes. For square root functions, it's continuous for all x where ax plus b is greater than or equal to 0, and ax plus b is your radicand. So remember, you can only take the square root of positive numbers and 0. For exponential equations, it's continuous for all x. For logarithmic equations, it's continuous for all x that are greater than 0, because remember the domain for log functions is all positive numbers. You can't take the log of 0 or negative numbers. Okay. In this next example, we're going to find all values x equals a where the function is discontinuous. Okay. So here I have a rational function. So what I need to do is pay attention to the denominator. And I'm going to take that denominator and I'm going to set it equal to 0. And I get x equals 7/2. So that tells me that the function is discontinuous at x equals 7/2. Because that would cause the denominator to be 0, which would make it undefined. Letter B, I have an exponential function. And exponential functions are continuous for all x. So they're not discontinuous anywhere. Okay, you can pause the video and try the next problem. And then unpause when you're ready to try example 4. In example 4, we have a piecewise function. We looked at piecewise functions in one of the previous videos. Here we want to find all values of x where the piecewise function is discontinuous. So something to point out, right? If you look at this piecewise function, each of these little pieces are polynomials. So that tells me that each of them is continuous. However, as you can see here, at x equals 1 and x equals 3, the function switches, and we could have a discontinuity. You can see that in the picture here, right? So there's a break in the graph. So we want to check each of those values. We want to check x equals 1, and then we also want to check x equals 3. Let's check x equals 1 first. Okay, so the first thing I'm going to do for continuity, right, I'm going to check f of 1 So for f of 1, I'm going to use this function because it tells me my domain is from 1 to 3 inclusive. So I'm going to evaluate that function at x equals 1. And when I do that, I get 2. The next thing I want to check is the limit as x approaches 1 from the left. And then I also want to check the limit as x approaches 1 from the right. Okay, so let's talk about 1 from the left first. So 1 from the left means that I'm going to use this function because if you're approaching 1 from the left, you're going to be using x values less than 1. So I need to use this function. So that's just going to be x plus 1. So let's write it like this. Okay, so this is just going to be, if I plug in 1, 1 plus 1 gives me 2. And then we're going to look at the limit as x approaches 1 from the right of f of x. So if I'm approaching 1 from the right, I'm going to be using this function again. So that's just going to be the limit as x approaches 1 from the right of x squared minus 3x plus 4. And if I substitute 1 in, of course, I know I get 2, and I know that from here. So the last thing I need to check for continuity is I need to see if what I got in the first bullet is the same as what I got in the second bullet. And of course, let me point out to you, since both of the one-sided limits are the same, remember we can say that the limit as x approaches 1 of f of x just equals 2. So therefore, this is, they are equal. So therefore, at x equals 1, the function is continuous. Okay. Now we're going to check x equals 3. So let me shrink that. Okay. So for x equals 3, we're going to do the same thing. We're going to first check f of 3. Okay, so we know that the function equals 3 here at x squared minus 3x plus 4. And if we plug in 3, we should just get 4. And then I'm going to plug in the limit as x approaches 3 from the left of f of x. Okay, and if I'm approaching 3 from the left, I'm going to be using this function, x squared minus 3x plus 4. Okay, and then the limit as x approaches 3 from the right. So if I'm approaching 3 from the right, I'm going to be using the 5 minus x. This 5 minus 3 gives me 2. So now if you notice, both one-sided limits didn't give me the same answer, right? So the limit doesn't exist. So therefore, that tells you right there that f of 3 doesn't equal the limit as x approaches 3, because the limit as x approaches 3 doesn't even exist. So therefore, let me add this in here. The limit as x approaches 3 of f of x does not exist. So therefore, the function is discontinuous at x equals 3. Here's another one for you all to try, so you can pause the video and try this one on your own, and then unpause when you're ready to move on. Let's look at a quick little application. So a trailer rental firm charges a flat $8 to rent a hitch. The trailer itself is rented for $22 per day or a fraction of a day. Let C of X represent the cost of renting a hitch and trailer for X days. So we want to graph C. But before we do that, let's make an equation, right? So here we're going to have a piecewise function because we are looking at X number of days, and X could be anything. So if I was to rent this hitch for one day, right, it's a flat $8 and then it's $22 per day. So if I'm renting it for the first day, it's going to be 8 plus 22 or $30. So C of X is going to equal 30 if X is less than or equal to 1 but greater than 0. Okay, now if I rent it for 2 days, it's going to be 8 plus 2 times 22. So 2 times 22 is 44, plus 8 is 52. Okay, so that's the cost is going to be $52 if X is less than or equal to 2, right? But it could be any fraction of more than a day. So if it could be 1.5 days, they're going to charge you for 2 days. And then let's just do one more. So if I rent it for 3 days, it's 3 times 22, which is 66, plus 8, which is 74. So you've got $74 if X is less than or equal to 3, but greater than 2. Okay, and so on. So if I was to graph something like this, right, the cost obviously would be the y-axis, and then days would be along the x-axis because the cost depends on the number of days that you rent the hitch. And the number of days, let's go out to like 5 days. 1, 2, 3, 4, 2, 3, 4, 5. And then let's do up to 100. We'll count by fives. 10, 20, 30, 40. 40, and then 50, 60, 70, 80, 90, 100. Okay, so if I want to graph this first one, right, C of X equals 30, that's just going to be a horizontal line at 30 from 0 to 1. So I want to find 30. And I'm going to put an open circle here and a closed circle here. And that's just showing me that, that's just showing me that the cost of renting the trailer for one day, or even a fraction of that day, would be $30. So it could be for half of the day, it's still going to be $30, right? Obviously, if you rent it for 0 days, it's not going to cost you anything. Now, the next cost is 52. So I'm going to go up to 52. And this time I'm going to have an open circle on 1. And I'm going to go out to 2. And then for my next one, it's going to be 74. And then like that. And you could keep going if you wanted. Okay. But you can see here, it says find any values of X where C is discontinuous. Well, you can see that there's breaks on the graph, right? There's jumps at each of the X values. So it's discontinuous at X equals 1, 2, 3, etc. Basically for all of the positive integers. Okay, you could continue the graph forever and ever, and you're going to get these steps. One application of continuity is what's called the intermediate value theorem, which we're going to look at more in depth later in the course. But basically, I'll summarize that for you. It says if a function is continuous on a closed interval, and we'll call that closed interval AB. We talked about closed intervals, right? A function's continuous on a closed interval, remember, when it's continuous on the open interval, and then when you check the limit from the right and the limit from the left. The function takes on every value between f of a and f of b. So let me give you an example of what I mean by that. Let's say f of 1 equals 3. Let's say negative 3. And f of 2 equals 5. The intermediate value theorem tells us that that function must take on every value between negative 3 and 5 as x varies over the interval 1 to 2. So in other words, let's say you have this picture, right? And we're only looking at from where x equals 1 to where x equals 2. Okay, and we know f of 1 is negative 3. And we know f of 2 is 5. So maybe the function even looks like this. Okay. If f of 1 equals negative 3 and f of 2 equals positive 5, then that function must take on every value between negative 3 and 5, which it does. You can see here, right? Because the function's continuous on that closed interval. So in other words, like f of 1.01 will have a y value, and f of 1.5 will have a y value, and so on. Okay, or it'll have more than one y value, but it's going to take on every value between negative 3 and 5. And that's it for this lesson. If anybody has any questions, please feel free to reach out to me. Hope you all enjoy the rest of your day.